Welcome to Maths with EJD. In this video, I'll be talking about canonical forms and classification of second order linear PDEs. I think this is the sixth video. The first five videos, I think four of the first five or so bordered a lot on first order differential equations where we saw method of characteristics and all of that. But here we switch over to second order linear partial differential equations, we talk about the canonical forms and their classifications. Okay, so first of all, um, let's have an overview as usual. We know that second order, a general second order linear partial differential equation in two variables x, y, looks like this. Now we've seen this a couple of times. It's a of x comma y uxx, that's partial u partial x squared, plus 2b of xy uxy, that's partial u partial squared u partial x partial y. That is, then we have plus c of xy, then uyy. Okay. That is partial squared u partial y squared. And then we have that added to order lower order terms. So basically, it means that these ones that have been indicated are what determine the classification of your equation. So the lower order terms don't really matter as far as classifications are concerned. But the lower order terms definitely will affect results for sure. Okay. So now that that is sorted, we need to know where uxx, uxy, uyy are partial derivatives, second partial derivatives. Then a, b, and c, a, b, c are functions. They are functions of x comma y. And we compute a discriminant based on this, but that's when we get to classification. So the classification is based on this A, B, and C. So let's talk about classification now. Classification. Okay. So the nature of the PDE, the nature of any partial differential equation is determined by the discriminant. The discriminant is D, and that is equal to B squared minus AC. This is crucial. I mean, we've done something about this in the second video, I think. So revisiting it is not a bad idea at all. So we have this now. So now let's look at type. What is the condition based on that D? And then we can have example. Okay, so first of all, we have an elliptic partial differential equation where D is less than 0. That is B squared minus AC is less than 0. And a very good example of that is the Laplace's equation. Laplace equation, which is uxx plus uyy equals 0. Okay. We have that. Then we move on to the next. So the next one is parabolic. So you have a parabolic partial differential equation where D is equal to 0. I did some examples to show this, to show each of them in the second video, I believe. So you have the heat equation in this case, which is parabolic. And here you have UT equals UXX. So it's parabolic in nature. And then we have hyperbolic. You have a hyperbolic partial differential equation where d is greater than 0. D is greater than 0. And a very good example of that is the wave equation. Wave equation. So for wave equation, you have that u t t, that's partial squared u partial t squared, is equal to c squared u x x. C squared u x x. So that is hyperbolic in nature. So that's the summary of that classification. Now let's move on to the next thing, talking about canonical forms. Um, so let's talk about canonical forms now. Canonical forms. Or I think I want to switch over here. Let's switch. Let's move to this now. This, and then maybe this can now be this. So talking about canonical forms. Okay. So by a suitable change of variables, the variables we have been talking about are x and y as independent variables and u as dependent variable. So by a suitable change of those variables now, by a suitable change of variables, say instead of x and y, we now have psi. I hope I can write this well. Mm, so you now have psi. At least I have issues with this. Okay, you have this one, two. Okay, you have psi and eta. Okay, so the PDE can often be simplified. It can often be simplified to the following. First of all, for something hyperbolic, for something hyperbolic, you can have u u psi eta equals 0. Okay, that's easily simplified. And then you can have, for something parabolic, you have u psi this is serious, u psi equals 0 for parabolic. And lastly, for something elliptic, when it's elliptic, you can have u psi plus u eta equals 0. So this is a process of simplifying some of these things. So the goal is actually to eliminate the mixed derivative or simplify coefficients. So the goal, okay, the goal in that case, goal the goal is to eliminate the mixed derivative, or simplify coefficients. Of course, from everything we've been doing, right? What this simply means is that this is now, for hyperbolic, now this is now partial squared u, partial psi, I, partial psi, okay, partial eta equals 0. And this means that partial squared u, partial psi, partial, uh, this now, okay, partial, don't know why this is so difficult for me, equals 0. And of course, this simply means we have partial squared u, partial this, 1, 2, partial squared eta, rather, plus partial squared u, partial squared, partial squared side, then partial squared eta equals 0. That's what all of those actually mean. So the goal basically is to eliminate the mixed derivative or simplify coefficients, as we saw there. Okay, so let's see some examples. Let's see examples. Or let me just say example 1. example one. I guess I want to switch over here. Okay, so here now let's go for this, and then I can use that on black. So let's go for example one. So example one, we have a hyperbolic case, hyperbolic for simple wave equation, which is hyperbolic. So given uxx minus uyy equals 0. So here we see that if you arrange it based on the standard, right? So if you arrange it based on the standard, you have something uxx plus. So if you arrange it based on the standard, like I said, so you should have something uxx, all right, plus 0, since the other one does not exist, 0 uxy, right, plus, now it's even minus. So that's minus uyy and other terms equals 0. So here now we can easily identify, we know that here, A of course is equal to 1, B is equal to 0. So this is the coefficient here is 1, then this is 0, and then C is equal to minus 1. So in that case, the discriminant is such that D is equal to B squared minus AC. So that means that D is equal to 0 squared minus 1 minus 1 times minus 1. So D is equal to 0 plus 1. And that means that D is equal to 1, which is greater than 0. So that establishes the fact that it is hyperbolic. Okay. Now talking about change of variables now. So change of variables. So for change of variables now, we say let psi be equal to x plus y, and let eta be x minus y. Okay. So we want to replace all the x with y's, right? So we now have to transform the derivative. So what do we do here? Uxx minus uyy. Okay. So uxx. So this case is right now. We have of course putting the two together, we know that simply when we add the two, I'm trying to get this the way it should really be. Okay. All right. So if you transform derivatives, so we have uxx minus uyy, uxx minus uyy will be equal to 4 u psi eta, 4 u psi eta. In that case, of course, this is equal to 0 already, right? So we have 4 u psi eta. So thus, the canonical form is u psi eta equals 0. Okay. So now that we have the canonical form, and we can see the general solution. General solution is now u of psi eta equals f of psi plus g of eta. All right. or that can also be given as u of x comma y equals f of x plus y, because this is x plus y and this is x minus y, then plus g of x minus y. So this is another way of representing that. Now, in the last example, I'm going to now the process of getting this for u eta for u psi eta is a very lengthy one. But in the last example, I'm going to show that process so that you can really understand how this came about. It's a very long process, but I'll explain when I get to that side, to that part. Okay. So that's example one right there. Let's take another another example two without showing the lengthy step before until we get to that last part. So example two. So for example two now, we have an elliptic situation where we talk about the Laplace equation. The Laplace equation. So in this case, we have this given uxx plus uyy equals 0. If you arrange it in that standard form, right, this will be uxx plus 0 uxy plus uyy equals 0, right? So that simply means that A is equal to 1, B is equal to 0, and C is equal to 1. So if you get the discriminant, so the discriminant is such that we have D equals B squared minus AC. So that's D equals 0 squared minus 1 into minus 1. So D is equal to 0 minus 1. So D is minus 1. And that is less than 0. So that automatically makes it an elliptic partial differential equation. And so, and with the way it is already in canonical form. So we have uxx plus uyy equals 0. So we can talk about a solution strategy for this. So solution strategy. So we can use separation of variables as we are going to see later. So use separation of variables or complex analysis methods. The complex analysis methods. Okay. So we'll see some of these methods later on. Then we have example 3. So for example 3, which is parabolic. So we have a heat equation corresponding to that heat equation. So for this now, given u of t equals uxx, so we can rearrange this to be uxx minus ut equals 0. In standard form, this is like uxx plus 0 uxy plus 0 uyy and minus ut equals 0. So from here now, we simply just know that A is equal to 1, that's the coefficient of uxx, B is equal to 0, coefficient of uxy, C is equal to 0, coefficient of uyy. So from there, we can do the determinant. So, I mean, the discriminant rather, the discriminant. That was what I called it the other time. Discriminant. Yeah, it's discriminant for sure. So that is D equals B squared minus AC. So D is equal to 0 squared minus A, which is 1 into 0. So D is equal to 0 minus 0. So D is simply 0. D is 0, and that is parabolic. That is parabolic. So settled. So in that case, we can say it's already simplified. The way it is already simplified. Okay, since it's already simplified, we can talk about a solution strategy. So solution strategy in that case. So we are going to implement some of this in subsequent videos. So separation of variables still works. A separation of variables, or what we call similarity solutions. Similarity solutions. like when you have u of x and t equals square root 1 over root t f of x all over root t. Okay, so that's similarity solutions. So we'll see some of this later. Now, this is where I actually get to do something more elaborate, showing all the steps that should have been taken to get the final results. So this last example drives the whole point home. So I think it requires special attention. So let me bring in black here and, retain others the way they are. So let's have a more advanced example, removing the cross derivative. So let's say example 4. Example 4. Here we have a hyperbolic case. We have something hyperbolic, which talks about cross derivative present. Cross derivative present. That's where we have uxy. So you have cross derivative present. Cross derivative is where you have uxy, something like this. Okay, so that's this example. So you see, given uxx plus 4uxy plus 3uyy equals 0. So you see everything is there. So given this now, we see that a is equal to 1, the coefficient of uxx. Then b is equal to 4. Oh yeah, b, here 2b is equal to 4, right? Yeah, if you remember, 2b is equal to 4. I was almost forgetting that. So this 4 now is 2b. 4 is 2b. So that means 2b is equal to 4. And that implies that b on its own is equal to 2. So pay attention to that. It's easy to just call b 4. Then c is equal to 3. So we have this. So we can go for the discriminant. So the discriminant, as usual, the discriminant is such that b d is equal to b squared minus ac. I'm always tempted to write 4ac because of quadratic equations. So d now is 2 squared minus a, which is 1, c, which is 3. So d is equal to 4 minus 3. So that d is equal to 1. And that means it's greater than 0. And that means that it's hyperbolic. So once it's greater than 0, greater than 0, it's hyperbolic. So from there now, we can begin to take some steps. So the first step we want to take, this we should have done this for the very first example to show it's a very lengthy process to get the u eta u psi eta. It's not as easy to come by. So we go for the characteristic curves. Find characteristic curves. So in this case, we cannot escape it. So from generally, right, if you have for the equation itself, remember the general format of the equation is let me see, let me try to remember. It shouldn't be this hard to okay, yeah. The general form, like we know it, is that a of let me just write a for that, right? So that's a uxx plus 2b uxy plus c uyy and all the other terms which don't really matter when we come to classification. So because of this now, this is basically a partial squared u partial x squared plus 2b partial squared u partial x partial y. This is the cross derivative we talked about. Then c partial squared u partial y squared and whatever terms you have, and that is equal to 0. So if you want to find the characteristic curves now, what do we do? That's the showdown we are going to have here now. So to find the characteristic curves, so what we now do is this. We have, so for this a now, this is partial squared u partial x squared. So uh we just call that dy all squared. Then we have plus 2b. So partial squared u partial y, we now call that dx dy. Okay. And then lastly, we have plus c into partial x all squared again. So with this case now, we can, so this is now equal to 0. So if you relate it with the original equation we have now, so if we compare this with the equation we are given in our problem, which is uxx plus 4uxy plus 3x plus 3uyy equals 0. So if you follow that, so it means we are simply just going to have, so that'll be, so for uxs now, we have 1 into dy squared plus 4 into dx dy, 4 into dx times dy, then 3 into dx all squared equals 0. So in this case now, what do we do next? So we can say let p be equal to dy dx. Okay, so if p is dy dx, so that means that we have p is dy dx, right? So we have, that simply implies that we have p squared minus 4p plus 3 equals 0. So that means if we divide through by dx, I think let me do that so I don't, that doesn't fly over our heads. So let's divide through by dx. So if we, in fact, we are dividing through by dx squared because we want to free up this, right? So if you divide through by dx now, the dx enters the bracket. So we have dy squared all over dx squared plus 4 dx dy all over dx squared, then plus 3 dx squared all over dx all squared equals 0. So this cancels this. So this cancels one of this. So we now have dy dx all squared plus 4 dy dx plus 3 equals 0. So this is a crucial thing that we can make reference to. So we can now say, let p be equal to dy dx. So if p is equal to dy dx, so it means that this whole expression now can now be p squared plus p squared, it should be, what's the original expression again? Yeah, the original expression is plus, right? Not minus, yeah? Does that affect any sign? Okay, so the dy dx, the original expression, the original, very original expression is plus. But by the time we do this transformation, I think because c is minus, is that a reason now? So in this case, we have a sign change happening here. So 2b now becomes negative. Okay, let me really confirm that. I want to be sure of that. I want to be very sure of that process. Does it become negative automatically? Okay, we have the original expression. And then by the time we do the transformation, it becomes negative. Okay, it becomes negative. All right, so we have to be careful with this. So where did I have that now? So when when this characteristic thing happens, this place becomes negative. So, and that automatically affects this place, making it negative also. So we keep going with that negative. So this is negative. So again, this is negative. So that's when that transformation comes along with that. So again, this is negative. So once we do that characteristic thing, that 2b part that was positive originally becomes negative. So with this now we can have, so if p is dy dx, so we have p squared. So this is like p squared minus 4p plus 3. So we have p squared uh p squared. Okay, let me go back to where I was coming from. P squared minus 4p plus 3. P squared minus 4p plus 3 equals 0. So if that is the case, we can easily factorize it. That is p minus 1 into p minus 3 equals 0. So that tells us that p is equal to 1 or p is equal to 3 easily. So we can then say thus, the characteristic curves, that's what we've been looking for. The characteristic curves are, so for y, we have y equals x plus a constant. All right, y equals x plus a constant. Uh, if, okay, to really make it cool, so what if we call this, let's call this P1 and call this P2, so I can follow logically, so you can see why this is happening. So we have y equals P1x, we have y equals P1x plus a constant, and another one is y equals P2x plus another constant plus a constant 2. So in that case now, we just have y equals p1 is 1, so x plus constant, okay, and y equals p2 is 3, so 3x plus another constant, okay. So we have this crucial one. So these are the characteristic curves. So we go for step 2 now. So step 2. So for step 2, we need new variables. We are transforming into canonical form. So we now need new variables now. So what would the new variables be? We have psi equals y minus x. Okay, psi is y minus x. And I think this is coming from here. So y minus x, and we have y minus 3x here. So we have y minus x coming from here to be psi. And then we have y minus 3x here. That will be our eta. Okay, that's where that is coming from. So we have psi equals y minus x, and then we have eta equals y minus 3x. Okay, so this is another crucial expression that we need. So if you now use chain rule, using chain rule, if you don't know chain rule, that's I treated that under basic calculus. So if you use chain rule, if you do partial x, generally, partial x, that will be, so if we do partial x, so we're saying, if we differentiate this one with respect to x now, so that will be minus partial psi, okay, because of this. So partial x, so that's minus part, because yeah, partial x in short, because partial psi partial x normally would be minus 1. So if you reverse it, so we have partial x, that's minus partial psi, minus, when we come here, if you differentiate x here, you have minus 3 partial eta. Okay, that goes. And then for the other one, if you do partial y, so partial y, that will be equal to, here you see partial y will just be partial psi. Okay, then if we come here now, we're still talking about y. Partial y here will just give us, because partial y partial eta, it will just be partial eta partial y is 1. So it means we just have partial eta, from here. So with that in place now, we substitute back. So substituting back, okay, the second order, PDE simplifies to, okay, here we are jumping a lot, so let me see how to do how not to jump, and and not waste time at the same time. Okay. I want to really make sure it's as clear as can be. Okay. Um, so we have used chain rule there. So we have partial. Okay. So we now applying the chain rule. We've done that. Okay, I think I'll just I'm trying to think, what should I do? I want to do my best so that this can be as clear as possible. Mm, trying to do that. Partial u, partial x will be all this. Yeah. Okay. 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 So, I mean, what this is simply telling us is that if we take it back to the original expression, if we take it back to the original expression, this is what we get. So substituting the second order PDE, so substituting back into the second order PDE, we it simplifies to the next thing. Let's see that now. Um, that's a more advanced example. Okay, let me see if I can make it more elaborate. Make Okay, let's see how we get on with that. So because I want to really make it as clear as can be. So substituting back the second order PDE simplifies to. So I don't want to jump that. I want to be sure how that comes along. Okay. Yeah, we're good with this. So, um, yeah, so what we have around here, we have partial x. Okay. Yeah, I want to go back here and really make it good, so that we can get it once and for all. So I don't just keep jumping. Okay. So now what do we have here? So we have, so from here now, we have all of this, y minus uh all this. So it means that psi here is taking the place of this constant. So this constant, and we also have this taking the place of that constant. So what we are basically now doing here is to use chain rule to get the derivatives. So we know for this we have partial psi, partial x. Partial psi, partial x here will just be partial psi, partial x will be minus 1. Then partial psi, partial y is equal to 1. That's from here. Then if we, that is, this one now is linked with this. So if we take this one now, so we know so partial eta, partial x is equal to minus 3. And then we know that partial eta, partial y is equal to 1. So we have this also. So what does that lead us to? It leads us to the fact that we take the first derivatives of u. So the first derivatives of u, what did it tell us? It tells us that u of x is equal to u of psi, u of psi, partial psi, partial x plus u of eta partial eta partial x. And then this also tells us that u sub y is u psi, then partial psi, okay, partial psi, partial y, plus u of eta, partial psi, partial y, okay? So if we have all this put together, then we can sort all of these things out. So for u of x now, so we have u of x equals, um, partial psi partial x that we got here, partial psi partial x is minus 1. So we have minus u of psi, because this partial psi partial x now is minus 1. Then plus u eta. Okay, we have u eta, then partial psi partial x. Partial psi partial x here is minus 3. So that's minus 3. So this is minus 3 u eta, because partial psi partial x is minus 3. So we have minus 3 u eta. So this is what we have now. Then when we come to this other side, we have uy. So partial psi partial y. Partial psi partial y is 1 here. So we have u psi. I'm back with that trouble of psi again. U psi plus partial psi partial y. Partial psi partial y is 1 again. So we have u psi and u eta. Okay? U psi, u eta. So this is settled now. Then we go for the second derivatives again. So for the second derivatives now, we also need to apply chain rule. So this is now second derivatives. So for second derivatives, we have uxx equals the ux we had before, and we differentiate that with respect to x again. So that ux already was minus u this minus 3 u eta with respect to x. But of course, we have to use chain rule again for this. So if we use chain rule, that is going to end up giving us, I'm trying to, I don't want to, okay. I guess I just need to, let me jump to the end now. So if you do all this, it's a complicated process from here because we are going to use chain rule. So here we have 9u psi psi plus 6u psi eta plus u eta eta. That is what that uxs gives us. So we do the same thing for uyy. Similarly, what do we have? Uyy would be, so that's the ui we had already. Uy differentiated with respect to y again. And that implies that what is our ui already? Ui is u psi plus u eta. So u psi plus u eta with respect to y. And that is going to be a chain thing. So at the end of the day, if you go through the whole chain rule thing, so we have uyy to be u psi psi plus 2u psi eta plus u eta eta. So this process is a lengthy one. The chain rule thing is a lengthy thing, actually. So we have all of this now. So we also need the same thing for, so also we have uxy. So uxy, that is ux with respect to y. So we already have, we know ux again is, what is my ux here? It's u minus u psi minus 3u eta. So minus u psi minus 3u eta, like this, with respect to y. So another chain rule, lengthy process, but then I can jump to the results. Uxy here is minus 3u psi psi minus 4u psi eta minus u eta eta. Okay. lengthy thing. So once that all of that is done, then we can move on to the next thing. So we go for that's my step. What so far? It's been such a lengthy step. That's just step one. Okay, we go for step two now. So step two. Step two. Okay, I think this should have all these derivatives part now is step two. So this is my step two. Step two, we express derivatives. From everything we've got, express derivatives. Or in fact, it should start from new variables. Yeah, we have new variables now. And then after the new variables, so let me just call this step three. So this is step three. This is step three. So I'll call the next one step four. It can be neater than that for sure, but let's use what we have for now. This is step four now. Okay, so we have step four. So for step four, we can now talk about we can substitute into the original PDE, So, and that is UXX plus 4UXY plus 3UYY equals 0. So, and we have all these expressions already. Okay. So UXX, we know UXX is up there. So I'll just continue with that. So we have for UXX now, we have 9U psi plus 6U psi eta plus U eta eta. That's just for only this. Then plus 4 uxy now is minus 3u psi minus 4u psi eta minus u eta eta. And lastly, we have plus 3 u eta eta. So u eta eta, that's u psi plus 2u psi eta plus u eta eta. And all of that is equal to 0. Lengthy, right? So if we group like terms, so group like terms. So if we group like terms, we see that for u eta, so we have 9 minus 12 plus 3 for u psi, okay, on the right hand side. So u psi 9 minus 3, 4 times 3, that's minus 12 plus 3, and that is equal to 0 u psi on the right hand side. So at the end of the day, that's what we have. So if we tidy this up, this is 9 plus 3, 12. Okay. Yeah, everything. So this is gone. We don't have anything to do with that. So next one we have for u psi eta, we have 6 minus 16 plus 6 u psi eta, and that is equal to, on the right hand side, so we have psi eta, right? So for like terms, so we have psi eta, just 6 minus 14, and here we have plus 6. And on the right hand side, that is minus 4u. Okay, I mean, this is 0 for sure. So now this is minus 4u psi eta equals 0. That means that u psi eta is equal to 0. So we have that. You know, this is not this was just 0 all the way, so we couldn't get anything out of that for sure. So the next one is now, so I think that's the only thing we can get. The other one is u eta eta. So for u eta eta, we have 1 minus 4 plus 3 u eta eta, and on the other side we have u eta eta. So this is 0 already. This is 0, just like this was 0. We couldn't get anything out of that. So this is also out of it. So the only tangible thing we get out is the fact that u psi eta is equal to 0. Okay. And once that is done, we can conclude that thus the PD reduces to u eta u psi eta equals 0, okay, which is the canonical form for a hyperbolic equation, just like we saw when we started out, right? So it's a lengthy process. I even had to jump some of the steps. Okay, so that's how that works. Yeah, so that's the idea of canonical form. So it's a pretty lengthy process. So you want to just you want to practice that. If you need to use it a lot, you need to practice, practice, practice. So you get used to the process. Okay. So with that in place now, the general solution of this, so for this kind of thing, general solution, in this case, the general solution is usually given as u of psi, comma, eta equals f of psi plus g of eta, or if you want to talk about it in terms of x and y, so u of xy would usually be f of y minus x plus g of y minus 3x. So for that particular problem, so you can have it in terms of eta, psi and eta, or in terms of y and x, like this, based on the things we got. So remember that constant thing, we have y minus x, and this is y minus 3x. So let's talk about a summary for all the things you have done. So let me switch this over here and probably have blue. Okay, so in summary, right? Summary. So what do you do? How do you take care of canonical form? The first step is identify coefficients, A, B, C, and compute discriminant D. That's the first step, because you want to know whether it is hyperbolic or whatever it is. Then step 2 is to classify. So based on that, you now classify PDE, whether it is elliptic, parabolic, or hyperbolic. That's the next thing you want to do. Then step 3, you want to find characteristic curves. You want to find characteristic curves if uxy is present. So once you have cross derivatives like that, you want to find the characteristic curve. So number 4, you introduce new variables, psi and eta. Introduce new variables psi and eta. New variables psi and eta. Then number 5, simplify the PDE to canonical form. Canonical form. And number 6, solve the simplified PDE, by collecting like terms. Solve the simplified PDE, and that is what we have. Okay, so based on this now, I can give a couple of questions. Okay, let's go for that. Practice now. Practice. So first, classify the following PDs. Of course, you know the classes, right? Is it elliptic? Is it parabolic? Is it canonic? Is it hyperbolic? So you have 3uxx plus 4uxy plus uyy equals 0. B, you have uxx plus 2uxy plus uyy equals 0. Then C, uxx plus uyy equals 0. Then D, you have uxx minus 4uxy plus 4uyy equals 0. Now, another one. This is question 1, if you like. This is question 1. Then question 2. Question 2 now. For each PD below, okay, 1, find the discriminant. Find the discriminant. D equals B squared minus AC. 2, find the characteristic equations. Find the characteristic equations. 3, suggest a change of variables. Suggest a change of variables like eta and psi. Psi and eta suggest a change of variables to simplify the PDE. And which PDEs are you talking about? The following. So the first one, you have uxx minus 6uxy plus 9uyy equals 0. Then B, you have uxx plus 4uxy plus 3uyy equals 0. You also have this uxx plus 2uxy. And usually the reason why we do this is once it's in a form where it doesn't have mixed derivatives. So that's how this is. It's been a lengthy one and it's fine. So be sure to try this out. Let me see your answers in the comment section, either on YouTube or on Facebook, right? And of course, let me also know how helpful these videos are for you. And if you have a problem you'd like me to solve or a topic you'd like me to treat, please feel free to let me know also. Apart from that, if you have subscribed to this channel, thank you. If you have not, please go ahead and subscribe. And don't forget to hit the notification bell so you can always get alerted each time a new video is released. And be sure to like and share so that more people can have access to this great content we have here. Till I come your way again, keep doing maths right. Bye.